Welcome back to che205. In this video, I'll be continuing on the solution of a system using the matrix rank. So we talked about section 375 in the textbook. In this video, we're going to focus on the case that rank of A is equal to rank of A augmented with B, but both are less than n, which is the number of unknowns, let's say. Not number of equations, because I realize that it could be confusing, so I'm going to stick with the definition of n to be the number of unknowns. So I'm going to show you an example of how many or how we can find the infinite number of solutions. So we know that this is the case that there's more than one solution, and indeed there is there's infinite number of them. Okay, so let's go back to the spreadsheet, and all right, so let me open my spreadsheet and then do a quick example to show you how we can find these n-r parameter family of solution. N, by the way, is the number of unknowns or variables you want to find, and R is, the rank of A augmented B. Both are called R. So you subtract R from n, and the result would be, and the solution would depend on this many parameters. Okay, so let me see why my Excel doesn't show up here. Close that. Okay, more links. All right. Okay. So, all right. So this is the spreadsheet from before. I'm gonna give you another example here. So let's say I have a system of equations like this: 1 plus 1x, 1 times x plus 1 times y plus 1 times z. And that is equal to 3. And then the next equation is 2x plus 1 times y plus 1 times z. And that is equal to 4. Okay, so I'm going to solve this system, and we know that this has more than one solution off the top of our head because we have 3 variables, 2 equations, right? So we know that from maybe in calculus, this system has more than one solution. One way to do this is you're going to fix one of the variables. You have 3 variables, so you're going to fix one of them. Let's say I put some value for x and then solve for y and z. Then I change my x, I can solve for y and z. So you see that for every x I put in, I can solve for y and z. Or maybe actually the other way around. So I'm going to put some value for z and then solve for x and y, right? Which I'm going to do now. So let's do this way. If you want to make sure that this has infinite number of solutions, let's create the matrix of coefficients. So it's 1, 1, 1, and then 2, 1, 1, and then the right side is 3, 4. So we're going to use our matrix package. You see that again, it's not here, and unfortunately that's the case. Every time you run Excel, if you don't see that blue button in Mac version, or in Windows version, if you don't see this macro sitting here, then you have to reinstall it. And that's not a big deal, it's really quick. You go to add-ins, select, and then you refer to the location of the package, which in my case is here, and then say yes, because we're reinstalling it. Okay, and all right, so the package is ready. I'm going to click on that, move this over here, macros, matrix operations. I'm going to do SVD, and my input matrix is this 2 by 3 matrix. The result will go to this cell and then run. Okay, so the rank, let's see here. So I'm going to close this guy and then say rank of A is 2 for now. Okay, and I'm going to do rank of A augmented with B. So again, macros operations, SVD, move it over, click on the matrix A. Now this time we're going to click on this 2 by 4. Okay, I'm going to include the right hand side of my equation, which is 3 and 4. And the result will go to this cell, and then click run. Alright, and then I see that the rank still is 2. So let me close that. So here rank of A augmented with B is 2. Alright. Make it a little bit larger. Alright. So the rank of A is equal to rank of A augmented with B, and both are 2 less than 3 because I have 3 unknowns, x, y, and z. So this is exactly case 3. This should have infinite number of solutions with n minus r parameter family. Let's look at how we can do that. So I'm gonna assume that z is known. If you think of z as a known value, then my equation would be x plus y is equal to 3 minus z, and then the second equation is x 2x plus y is equal to 4 minus z. Okay, right? So now you see that you put something for z, you get x and y. So you get 2 equations to unknown, you can solve this, right? So the equation for x and y given z is or has a unique solution. When you want to test that, you can easily calculate the rank of this A matrix now, which is 1, 1 on the first row and 2, 1 on the second row, and 3, something like 3 and 4 on the right side, but given z value, the right side can change. So anyways, if you do the rank of A and A augmented with B, then you would see that the rank of A is 2, rank of A augmented with B still is 2, and then the number of unknowns would be 2 again, so all of them are equal, and that means we're looking at case 2, which has a unique solution, right? So we're talking about this case. All right, so for every z you put in there, you get 1 x and 1 y. So this is called, so you can solve for x and y, and so you can easily, let's say you can easily subtract the 2 equations. And if you subtract the 2 equations, you get x is equal to 1, right? And then y would be equal to, so you plug in 1 in one of the equations. Let's say I'm going to put 1 in the first equation, and you get y equal to 2 minus z. So that's the solution. Let's test. I'm going to plug these 2 in the first equation. X plus y is 3 minus z. That's right. I'm going to plug x and y into the second equation. You get 2 plus 2. It's 4 minus z, and that satisfies the second one as well. So that means this is a solution, and you see that it depends on z, right? So this is called n minus r. So n is 3. R is the rank of A and A augmented with these 2. So 3 minus 2 is 1. So this is one parameter family solution, and that one parameter is the z, right? So again, n minus r in this case is 3 unknowns minus rank is 2, that is 1. So there should be one parameter family of solution because there's z here. So that z is the one parameter. So you see that how I took it out? So you assume z is known, you bring it to the right side, or you subtract z from both sides of these 2 equations, you get this, and then you assume that z is known, you solve for x and y only, which depend on z. Okay, so that is exactly the case 3. So I hope this is clear how we can do that. Now we're going to talk about, for a few minutes, the homogeneous case, ax equals 0. It's called homogeneous because the right side is 0. So whenever in equation ax equals b, the right side is 0, we call it homogeneous. Now this case is always consistent. Why? Let's look at the definition of consistent. Consistent is when the rank of A is equal to rank of A augmented with B. This is called consistent. If you forget, then you go back here, and the consistency by definition is if the rank of these two are equal. And because B is 0, right, if you calculate the rank of A, and you put 0 on the last column for A, and if you calculate the rank, you see that it's always equal. So rank of A is already equal to the rank of A augmented with B. Automatically, you don't need to do any modification. So that's always consistent. It has a trivial solution, yes, because if you put 0 here, you always get 0 equal to 0. So this is a trivial solution, which we are not interested in. We're interested in non-trivial solution. And then okay, so then we look at other solutions. Now, in the case that rank of A is equal to number of unknowns, okay, for this case, then the solution is unique, and that solution is the trivial solution. Okay, so the trivial solution is unique as long as the rank of A is equal to n number of unknowns. And then this case we just talked about, there is n minus r parameter family of solutions if the rank of A is less than n. So you see that this is actually a special case of that case. In case 3 here, we did have B, but in this case we don't have B because B is 0. So you don't see that B, contributes anything to these conditions. So it's always rank of A compared with n, right? So there's no rank of A augmented with B. Because B is 0, we don't put them in here. We don't put that in here, okay? Okay, so a special case is the homogeneous case, and if the rank of A is less than n, then this should have n minus r parameter family of the solutions. Okay? So we already talked about the case where there's no solution. There's no solution if rank of A is not equal to rank of A augmented with B. So that is the condition we considered before. Okay, so let me see. I hope this is clear. I can do one quick example for the homogeneous case where the solution is an infinite number of solution. Let me see if I can make it up. In this case, let's put 3 and 4 equal to 0, right? So I'm going to just duplicate this and show you here that in this case, well, rank of A is as before. Rank of A still is 2, right? So rank of A doesn't change because my A doesn't change. Rank of A augmented with B, I'm going to show that still is 2. So I'm going to test it here for you. Okay, so the matrix will be same as before, but the right side should be 0 and 0. All right, and then now if you do the matrix package and calculate the singular values of this A augmented with B, and then the result will be in that cell. You see that still is 2, right? The rank is still is 2, and this is less than the number of unknowns, so we know that there are infinite number of solutions, and the rest would be the same as here. The only difference is you put 3 and 4 equal to 0, so the solution would look something like this, where I have 0 here, so this goes away, and I have 0 here as well. So the solution would be, so x is going to be 0, and then y is equal to be minus z. So you see that there are still infinite number of solutions. If we want to make it even better, you want to write it as minus z. So there's still infinite number of solutions, and there's one parameter family, and that is z. So this is a homogeneous case where the right side is 0. Okay? Alright, so thanks all for watching. Stay tuned for the next video on matrix operation using Excel sheet.